Hello everyone. We're going to start a new subject, which is multi-phase flow, and we will discuss different topics from now on. These are new topics that we haven't talked about it, including the surface tension, interfacial tension, wettability, capillary pressure, and all these concepts will come basically into the topic of multi-phase flow. So the first thing that we're gonna discuss is some of the basic concepts of multi-phase flow. So the first thing is you need to know what is the phase. So in petroleum engineering, a phase could be a liquid, solid, or gas, and the way we define it is that they should have a identifiable boundary, right? So they should be separated from each other. For example, you have oil and water in the porous media. Oil is a phase, water is another phase. You can say in general that you can have different types of phase that you have heard maybe in thermodynamics that are solids, liquids, or gas. But in petroleum engineering, we don't necessarily say that all the liquids are separate phases. The property that they should have is that they should have a boundary that you can separate from each other. For example, oil and water don't mix, right? So they have a boundary between each other. But if you have, for example, a gas that is dissolved inside your oil and you can't separate it, then you can't really say that's a separate phase. So that's the definition of the phase, and there are many examples of that. You can basically discuss it. Raindrops in the air, raindrops are a phase and air is another phase. Many other basically definitions, but in porous media, that's how we define the phases. So we talked about this, and specifically these phases from the definition should be immiscible. So with the immiscible we mean that these two phases that we are discussing, they shouldn't be mixed with each other. So again, you might have gas, you might have liquid, and they shouldn't mix with each other. For example, consider that you have a surface and then you have water on the surface, and then you have oil here, right? So you can see that these two phases are separated with each other. So this is the boundary of the phase, two phases. Also, if you have a solid here, which is your rock, then solid is another phase, and solid have an identifiable boundary with water. Water have again a clear boundary with the oil. So these are three separate phases. Another consideration in petroleum engineering is that the phase that we basically model in our simulations is the phase that can move from one location to another location. So solids really, if they can't move, we don't consider them as a phase. And usually what we model in reservoir engineering is the water and oil, because these two components can move, right? So sometimes the water cannot move as well. So for example, consider that you have a porous media and then you have a pore. Let's assume that this is your pore, and there are some water here. So let's say this is water, I'm showing it with W, and then there is oil inside your system. Now this water, if this water is irreducible water, so let's assume this is your water, right? And this water is irreducible water, which means that it cannot move. Then but the oil can move, right? So the water here, again, this system is, although you have water and oil separated by a clear boundary, this system still is considered a single phase system. Why? Because the water cannot move. But if you have a water that can move, oil can move, then that's a two-phase system. So that's basically the definition of these phases. So what is important for us is basically how much of each phase we have. We define this by introducing the concept of saturation. And another important thing that affect how these fluids move in porous media is that how these fluids interact with each other. So if you have oil and water and solid inside your system, you have a fluid interaction. You have fluid 1 Reich interaction, and then you have fluid 2 Reich interaction. So fluid 1 could be water, fluid 2 could be oil, and these basically different phases would interact with each other. So this is important to understand how the interaction is, what forces and energies are involved during this process, and that's the topic that we're going to cover in next few weeks of this course. So the first concept that we need to discuss is the concept of surface and interfacial tension. You have seen that if you wax your car and it rains, the bubbles of the raindrop stick to the surface. If you have waxed your car, the shape of those bubbles are different when you have an unwaxed car, right? So for example, this picture shows the hood of a car, and that the hood is waxed, and you see that these bubbles stay pretty much spherical, or I should say squashed spheres are formed here on the surface of the hood. Now, if you don't wax the surface of your car, what you see is that these water liquid would spread over the surface, and it's not anymore like bubbles. So if I want to draw these two systems, let's say this is the hood of your car, right? And then the bubbles, the water bubbles may be something like this. This is the waxed hood. They don't stick to the surface, right? Because of the surface and interfacial tension. That's the concept we're going to discuss, okay? And consider that if you'd have unwaxed hood, then the water would spread over the surface. These are water. So there is a huge difference between these two, and it goes back to how the molecules of water and the molecules on the surface of the hood interact with each other. So what you will learn is the concept of surface tension, the concept of interfacial tension, and what is the difference between really a surface tension and interfacial tension. And then next we will talk about wettability and hopefully capillary pressure in next couple of weeks. So what is surface tension? So let's talk about just a single liquid. Let's say you have water, right? Water is composed of millions of molecules. These molecules have attraction force between each other, and they really like each other. So this attraction force between the molecules of a given liquid, such as water, is called cohesion force. Okay, so these two molecules, for example, in the water system, they are attracted to each other, they love each other, and this force or attraction between these two molecules is called cohesion force. Okay, so now if you have a liquid, let's say you have a bucket of liquid, right? So let's assume that we have a bucket of liquid water here, right? The molecules which are within your system inside the liquid, they attract each other, right? So for example, this specific molecule, there is attraction force with all the molecules surrounding it, right? So you have all these interaction forces. But what about the molecules on the surface? Is there any molecule on the top of these molecules that have interaction or attraction force? The answer is there are molecules, but those molecules are not liquid water anymore. They are air, right, on the top. So the attraction force is different, and we'll talk about this topic that air or any basically gas attraction force is very weak compared to liquid. So there is an imbalance force on the surface. You can see it in the next picture. There is an imbalance force at the surface of that liquid, which causes the surface to be squeezed, and an extra force is basically being applied to those that surface, which causes this surface to be squeezed. This force is called surface tension. Okay, surface tension is basically at the surface of the liquids, which there is an imbalance force, and it causes a film to be formed, kind of a film to be formed on the surface of the liquids. You might have seen this picture that if you have an insect that is sitting on the top of a liquid, it can walk on the liquid, on the surface of the liquid, right? The reason is the surface tension. The molecules on the surface have an imbalance force, which causes the surface to form a kind of a film, elastic film over the surface. So, however, if you put this insect, the legs of this insect inside the liquid, it can move very easily, right? Because there is a balance force inside, so there is no film or anything within the system. Anyway, so that's the definition of the surface tension, and the unit of the surface tension is force per unit length. So this dynes is the English unit for force. So that's force per unit length. That's the definition, or it could be energy per area. So both are okay, both are correct. Either energy per area or force per length. For water, usually is around 72.8 dynes per centimeter. Depends on the liquid. For alcohol is around 22. For mercury is really high. It's 465. So what does it mean? If your surface tension value is high, it means that you have a very high cohesive force between the molecules of that liquid. So mercury molecules really love each other. Ethyl alcohol molecules probably don't like each other much because the surface tension is very low. So the cohesive forces are small, right? But the mercury cohesive or basically cohesive force is really high. It means that there is a high attraction between the molecules of the same liquid. So that's the definition of surface tension. In the next video, I'm going to talk about the interfacial tension and adhesion forces.